Welcome to this session on pA2 values, a key concept in pharmacology. The pA2 value helps us to quantify competitive antagonism. It's a measure of the concentration of antagonist needed to double the amount of agonist required to produce the same effect. In this video, we'll explore what pA2 means, how it is measured, and how to interpret the results using Schild analysis. Let's begin with something familiar, the pH scale. pH ranges from 0 to 14, with low values indicating high acidity and high values indicating alkalinity. You'll remember that pH is defined as the negative logarithm of the hydrogen ion concentration. That is, pH equals minus log of hydrogen ion concentration. Now let's bring in the pA2 scale. Like pH, pA2 is also a logarithmic measure, but instead of hydrogen ions, it refers to the concentration of a competitive antagonist. Specifically, pA2 is the negative logarithm of the molar concentration of antagonist that causes a twofold shift in the agonist dose response curve. Let's highlight the common structure. The P in both pH and pA2 means minus log. In pH, the H stands for hydrogen ion concentration. In pA2, the A stands for antagonist concentration. So, just as a low hydrogen ion concentration gives a high pH, a low antagonist concentration gives a high pA2, indicating a potent antagonist. In summary, pA2 is equal to the negative logarithm to base 10 of the molar concentration of competitive antagonist that causes a doubling of the dose of agonist needed to produce the same response. To measure a pA2 value, the first thing we need to know is how much the antagonist shifts the agonist dose response curve. We start by recording responses to the agonist over a wide range of concentrations. Responses could be anything from muscle contraction to the product of an enzyme reaction. The example here is a typical organ bath experiment where the response is the contraction of smooth muscle. The amplitude of each response is measured. Then a plot constructed of the response on the y-axis against concentration on the x-axis. As often done, the responses here are plotted as a percentage of the maximum response achieved. A line connects the data points to complete the dose response curve. This is the control dose response curve in the absence of antagonist. Next, we determine the EC₅₀, the concentration that produces 50% of the maximum response. The experiment is then repeated in the presence of a fixed concentration of the antagonist, say 3 nanomolar. Responses to the agonist are measured and plotted on the same graph. The dose response curve shifts to the right because higher agonist concentrations are required to achieve the same effect. This means that the agonist EC₅₀ is higher than in control conditions. The magnitude of the shift is expressed as the dose ratio, or R. It's calculated by dividing the EC₅₀ measured in the presence of the antagonist by the original EC₅₀ measured in the absence of antagonist. The experiment is repeated at higher antagonist concentrations. EC₅₀s are measured and the dose ratio calculated for each antagonist concentration. A dose ratio of 1 means there is no change. The antagonist had no effect. But as the antagonist concentration increases, the dose ratio becomes larger, indicating that the antagonist is effectively competing with the agonist for receptor binding. It's important to collect several EC₅₀s and dose ratios for different antagonist concentrations. Now that we've measured the dose ratios, we can use those values to perform a Schild analysis, a classic way to quantify the potency of a competitive antagonist. The Schild equation relates the dose ratio R to the antagonist concentration in the following way. It states that the logarithm of the dose ratio minus 1 is equal to the logarithm of the concentration of B minus the logarithm of Kb. In the Schild equation, B refers to the antagonist and Kb is the dissociation constant for antagonist binding to the receptor. If we compare this with the familiar straight line equation, y equals mx plus c, the similarity is clear. The slope m is equal to 1, and the intercept gives us the antagonist's affinity. To apply the Schild equation to our data, we need to subtract 1 from the dose ratio at each antagonist concentration. Then take the log of each of these values. We also need to take the logarithm of each antagonist concentration. Now we can create a plot with log R minus 1 on the y-axis and log antagonist concentration on the x-axis. If the antagonist binds to the receptor in a reversible and competitive manner, the data should follow a linear relationship with slope equal to 1. The relationship here appears linear, but what is the slope? The slope is the change in y divided by the change in x. These dotted lines mark a 1-unit change on the y-axis. Extending them to the fitted line and dropping vertical lines to the x-axis shows that a 1-unit change in y corresponds to a 1-unit change in x, confirming the slope is 1. Finally, the point at which the line intersects the y-axis corresponds to minus log Kb. However, this intercept cannot be read directly here because it lies outside the visible range of the plot. Nevertheless, the graph can still be used to determine Kb. Consider the point where the dose ratio equals 2, meaning the concentration of agonist required to produce a given response is doubled. At this point, log R minus 1 equals log 1 equals 0, and rearranging the equation shows that the logarithm of the antagonist concentration equals log Kb. In other words, Kb is the antagonist concentration that produces a dose ratio of 2 for a given response. Therefore, drawing a horizontal line at y equals 0 for dose ratio equals 2, and projecting its intersection with the line down to the x-axis gives log Kb. In this example, log Kb is minus 8.75. The anti-logarithm is 10 to the minus 8.75, which equals 1.78 times 10 to the minus 9 molar. This tells you that 1.78 nanomolar antagonist is required to double the agonist concentration needed for the same response. Pharmacologists express this property as the pA2 value, which is defined as minus log Kb. Here, pA2 equals 8.75. In theory, the Schild plot for a competitive antagonist should be a straight line with a slope of 1. But in real experiments, that's not always what we see. The slope could be less than 1, or occasionally greater than 1, or the relationship may not be linear at all. If any of these situations occurs, it means that the data don't follow the assumptions of a simple reversible competitive interaction. In these cases, we can't use the x-intercept as a valid pA2 value because the Schild equation no longer accurately describes the system. There are several possible explanations. The antagonist might be non-competitive or bind irreversibly. It could act allosterically at a different site, or the preparation might not have reached equilibrium before measurements were taken. Whenever the plot is non-linear or has a slope not equal to 1, it's a signal to look more closely at the drug's mechanism of action rather than just its potency. So, while a perfect Schild plot gives us a clean pA2 value, a non-ideal one can reveal much more about the complex pharmacology of the receptor. So, what does the pA2 tell us? The pA2 is a direct measure of an antagonist's potency, how effectively it competes with an agonist for receptor binding. It's defined as the negative logarithm of the antagonist concentration that causes a twofold shift in the agonist dose response curve. In other words, it tells us the concentration of antagonist needed to double the agonist dose required for the same effect. On a Schild plot, when the slope equals 1, the x-intercept gives us the pA2 value. A higher pA2 value means the antagonist binds more tightly, has a lower dissociation constant, and is therefore more potent. Because it is independent of the agonist used, the pA2 provides a reliable way to compare antagonists acting on the same receptor system.